Hello,
Yes, sir.
am I audible?
Yes, sir. Yeah.
Is the PPT visible?
Yes, sir.
Okay. So very good morning. So at the outset, I would like to thank SRM University for giving me the opportunity to present the recent research on mitigation of earthquake-induced liquefaction risk by induced partial saturation. So my voice is clear?
Yes, sir. It's clear.
So I'm getting some echo. I hope my voice is clear.
Yes, sir. You can.
What is the allotted time for me? How much time I have to take?
Sir, 1 hour. It's-
1 hour.
Yeah.
Okay, thank you. So the topic is mitigation of earthquake-induced liquefaction risk by induced partial saturation. It's a new method which we have recently developed to basically overcome the issues related with earthquake-induced liquefaction. This is my presentation outline. I'll be briefly explaining about the mechanism of liquefaction, effect of liquefaction, and what are the current practice with respect to liquefaction mitigation. Start with a brief introduction about induced partial saturation. So basically, we have worked with the two methods, MIPS and the air injection method test. So I'll explain this research outcome and finally conclude about this research. So before moving to this topic, I just would like to know how many are attending, how many faculties are attending, how many are having background related with earthquake engineering or geotechnical earthquake engineering. Probably the host can give a very brief statistics of this program. Hello? Your voice is not audible, please louder. How many have registered? How many are doing PhD in that area of earthquake engineering or earthquake geotechnical engineering? What is the general distribution of the audience?
As we don't have that specific idea, it's FDP is like 300 participants are registered. They are faculty and PhD scholars.
Okay. Okay, anyway, fine. So I presume that the audience are basically from civil engineering background and working research in the area of sustainable engineering. Consists of all civil engineering field. You can, I mean, you can very well write your queries during the presentation in the chat box. After the presentation, we can have a discussion. Either you can directly post the question in the chat box, or you can allow them to ask the question directly.
Okay, sir.
Okay. So let us move on to this topic, soil liquefaction. Many of you very much aware about this soil liquefaction issue. It essentially triggered during the time of earthquake. It's one of the most critical issue occurred during the time of earthquake.
Excuse me, sir. Sorry to disturb you. Actually, sir, there are two systems over there from your side. There is some echo.
That is what I was asking.
Yes, sir. Yes.
Okay, give me some more time. I'll check it out.
Yeah. Take your time.
Am I audible now?
Yes, sir.
Sorry, actually, I have to join in both
Yeah.
user and admin. I'm sorry. I hope now it is clear to you.
Yes, sir. Now
The voice is clear. So
Yes.
just go ahead. This is a presentation outline I have already briefed. So just I'll briefly explain about the soil liquefaction phenomena. It is normally happening where you are talking about the loose deposited soil under the influence of seismic load or peak load. Soil particles are separated and pore pressure is increased. The increased pore pressure will try to reduce the effective overburden pressure of the soil, and thereby it is acting almost like a liquid. So your supporting system, existing building is resting on the soil, where the soil is already the state of liquid, subject to a huge failure in terms of settlement or overturning or sliding. So all is happening. So it is a very important aspect during the earthquake process, time of earthquake. So we need to mitigate this particular aspect during the process of earthquake. It is very, very critical aspects. So we need to have a proper mechanism to overcome this kind of liquefaction-induced failures on the structure. And there are several methods available to mitigate this liquefaction. But the one what we have developed is somewhat unique, and it is more sustainable and cost-effective technology. So with this small brief about the liquefaction process, let me go further. So you are all very well aware about the past earthquake induced several liquefaction induced problems. Several earthquake we have also seen and witnessed several catastrophic effect. And some of the earthquakes are severely created impact on the human life, and several life loss and building loss during this earthquake. Some of the photographs what you are seeing is the classical one. The left side what you are seeing is the Nikata earthquake in Japan, 1964. Classical example for liquefaction induced failure. And you can see here how the building is deflected or rotated. And even if you look at the close view of the building is not having any kind of major distress, but the building is completely collapsed, settled, or tilted because of the poor bearing capacity of the soil or earthquake-induced liquefaction in the soil. Several such kind of failures were noticed across the globe. It's all basically with respect to the soil structure interaction issue considered under the earthquake-induced forces, and especially where we are talking about loosely packed soil under saturated conditions. So that is triggered by earthquake created pore pressure, and the build pore pressure is not able to dissipate instantly because the period of earthquake shaking is very few seconds. Within the few seconds, the build pore pressure is not able to dissipate, and thereby the pore pressure is trying to reduce the effective overburden pressure of the soil, and the whole system is almost like a liquid state. So whatever the structure pour on that kind of soil, buildings are subjected to collapse. So just look at the Indian scenario. So, Indian Seismic Code IS 1893 was revised in 2002. India has a very vast coastline, about 7,500 kilometers, which signifies a high risk of liquefaction hazards. And more than 50% are vulnerable places. The study was witnessed along this coastline. And you're all very much aware that along the coastline, many of our metro cities have been located. More than 50% of these metro cities or metropolitans are subjected to liquefaction risk. So according to the outcomes, microzonation, including liquefaction hazards, around 63 cities in India having liquefaction sustainability. So it is very, very important to look into this mitigation of liquefaction. And moreover, we need to develop a system which will be a sustainable system in terms of all other perspectives. Just to have a conventional methods, what we are current practice, what we are doing for mitigating this kind of liquefaction soil. The traditional methods are conventionally we are going with dynamic compaction, vibro or deep compaction methods, grouting or stone column, foundation replacement or chemical stabilizations. These are some of the methods frequently we are using to mitigate the soil, and especially your weak soil, densify it by doing this kind of ground improvement techniques. So since we are talking about sustainability, since we are talking about environmental friendly techniques, the so-called techniques all induced a huge energy dissipation and also subject to utilization of natural resources. So because of that, and many of these methods are basically cement-based method. And this cement-based methods like deep soil mixing, grouting have a drawbacks, and emitting almost 147 tons of CO2 and consuming 11,74,000 kilojoules of energy. So you can imagine how much we are producing CO2 and how much energy is being consumed by these conventional methods. So it is not at all a sustainable method or environmentally friendly method, the so-called conventional techniques. So comparative analysis shows that alternative designs like reinforced concrete or T-wall have even higher energy consumption, because these methods, where this is an improvement method, where these are the permanent solution for mitigating the weak soil. But going with a permanent solution for using the cement-based structure, something like a reinforced concrete or T-wall, the consumption of energy is much higher and the emission of CO2 is much higher than the improvement method. So these methods, basically it is not environmentally friendly method and sustainable method. So, and moreover, these methods are having a lot of challenges, especially environmental challenges. As it is a limited field application, so non-biodegradability, and inappropriateness for a significant ground depth, vulnerability to low pH value, so ammonia byproduct, low economic feasibility, high sensitivity water, and severe hydrogen swelling. These are the long-term concern with respect to the existing method. And we are also using heavy machineries and materials. So we are using heavy machineries for material transport. So you can see some of this method what you have presented the right side. So all this basically is large energy consuming process as well as natural resources and cement based material, the cement manufacturing process, and consuming those cement based materials using in the ground, and so a lot of challenges. The possibility of impact on surrounding structure. So suppose the method what you are selecting, the existing conventional method, dynamic compaction or micro deep compaction, grouting stone column, or chemical stabilizations. If you are going with these methods are more appropriate where you are looking for a greenfield problem, new construction. In case if you are identified your subsoil is weak, substrata is weak, and during the earthquake time you may expect some sort of liquefaction, using these methods may have some impact on the existing structure. So the possibility of impact on surrounding infrastructure is expected for the conventional methods. And these methods basically are having high construction cost and rise of polluting the surrounding environment and even polluting the water body, and not applicable for existing structure and significant use of natural resources. So these are the some of the drawback with respect to the existing method. So we need to look into a method which will try to minimize all this aspect, and as well the method supposed to be useful for the existing structure. The one which we could be able to minimize all this, the environmental issues and the issues related with the impact of the existing structure and vibrations induced problems for the nearby structures or structures is close to the construction premises area. The one which is called induced partial saturation. So basically the issue of liquefaction is expected where you are talking about fully saturated soil mass, and especially the fully saturated soil mass with medium to loose densified state, and the soil is not having significant amount of fine content. It's prone to have a liquefaction during the time of earthquake. So if any soil, if you talk below water table, groundwater table, it's always subject to 100% saturation. So by a way of reducing this water content in the soil, we are bringing the soil from fully saturated to partially saturated soil. So that is the concept of induced partial saturation. So as it is, the soil is fully saturated below the water table, groundwater table, and the soil which consists of fine silty sand with the compactness state is loose to medium dense is prone to have a liquefaction, provided the soil is fully saturated, because all the white space is occupied with the water molecule. So somehow, if you are able to reduce the amount of water in the fully saturated soil, your soil becomes partially saturated, then the possibility of liquefaction successibility or liquefaction potential is reduced. So that is the idea of induced partial saturation. So liquefaction risk mitigation planning, design and execution concerning an innovative ground movement called induced partial saturation. So basically we are trying to introduce some sort of air bubbles, gas into the voids of the soil. So partial saturation can be increased to increase the resistance to liquefaction susceptibility, and environment friendly, economical, applicable without affecting any nearby structure, and applicable under existing structure. So these are the some of the advantages with respect to induced partial saturation process. But the big challenge is how to obtain the induced partial saturation, the partial saturation in the soil is $1 billion. So we need to have a very, very systematic procedure, such a way that the developed procedures would be able to bring out the soil in the partial saturated state, and thereby we could be able to reduce the liquefaction risk. So that is the idea of this particular topic. I'll just go back to a little bit of theoretical background about partial saturation or saturated soil or unsaturated soil. Some of you very much aware about the mechanism of saturated, unsaturated, fully saturated, partially saturated strength mobilization mechanism. I'll just briefly explain about what is happening during the time of saturated state to unsaturated state. From the state unsaturated to saturated, how the strength mobilization is taking place, what are the benefits that we are getting from this soil mechanics point of view. In the unsaturated soil, the air phase persists the metric suction. So this you're all very much aware. This is the mechanism what we are expecting in unsaturated soil. So the soil will develop a metric suction. So because of the metric suction, the soil will have a capacity enhancement. So basically, once we decided the soil is partially saturated, you will have a two-component, two-phase system. It's a complete three-phase system in which the void space is partially filled with water and air voids. So you have a both combination of water and air voids within the system. So the mobilization will have, in terms of the resistance, comes through this water as well as air. So thereby your pore water pressure will have in terms of air pressure as well as water pressure. So you're all very well known that any pressure development is with respect to applied load. Suppose your applied load is sigma 0 or sigma naught, that is normally considered to be initial pore burden pressure of the soil. So with respect to the incremental value of sigma, there will be a corresponding development of U, that is a pore pressure. So now your sigma is having two components, one is UA and UW. So where you have a air pressure, that is a pore air voids pressure as well as pore water pressure development. So we have a distinct two components. So the accumulated air bubbles will now alter the compressibility of pore fluid in partially saturated zone, but they will not interact with the soil structure. So this is the advantage what we are trying to gain from partially saturated soil. Suppose you are talking about fully saturated soil at the bottommost, where you are increasing your sigma 0, there will be a corresponding increment value of UW, pore pressure. So as the condition when the V reaches to 1, the applied external force is leading to increase equivalent to the applied pressure of pore pressure. So once the pore pressure is increased beyond that, so here sigma 0 is considered to be effective overburden pressure. So when U is increased close to overburden pressure, or if it is more than the overburden pressure, then your soil contacts will be destroyed by the force which is developed by the void space. So thereby your system is acting as an individual structure, not a connected structure. So your soil grains will float in water. So that is what is happening in fully saturated soil mass. Whereas in partially saturated soil mass, the same state where some of the waters have been replaced with the air bubbles. So what we call it as accumulated air bubbles. So these air bubbles having an advantage. So why there is an increase in pore pressure? Because of the dynamic effect. So since your system is subjected to oscillation, so the pressure is increased. Since the time is very short, we are talking about fine silty sandy soil. The pore pressure, developed pore pressure dissipation will not take place instantly. So thereby your pore pressure lifting the particles. So thereby your soil shear strength is lost. So the advantage of having accumulated air bubbles, so this will act as a cushion effect. these bubbles will have an accretion effect. So basically, you can talk in terms of the compressibility component, where you have only water, then as you know that water compressibility is almost insignificant, it won't compress. Rather, pressure will build and it will try to destroy the soil particles. When air bubbles are accumulated, air bubbles are formed within the system. So these air bubbles will act as an energy absorbent. So your soil, it will ensure that reduction in interaction between the particles, and it will compress more. So when the particles, the system, the white space are subjected to more compression, then development of pore pressure will be less. So if the pore pressure development is less, then the chance for liquefaction is reduced. So this is the simple mechanism. So this mechanism is not a new one. It is already established mechanism. So, but we want to create a system how to make the calculated air bubbles to keep that soil in a particular degree of saturation to maintain the liquefaction resistance for the soil. So this is what the whole background of this particular study. So we can just have a look of this pore air and pore water pressure variation with respect to the level of degree of saturation. So if it is a fully saturated soil, it is only with respect to the water pressure. This is a Skempton pore water pressure parameter B. So where we are considering, it is only governed by water pressure. And if it is unsaturated soil, it is only governed by the pore white space. And the zone between these, where we are talking about, the parameter is less than 1, partially saturated soil. So if it is fully saturated soil, you have risk of liquefaction. We are talking about this, the bottommost layer, we have more issues. If it is unsaturated soil, we don't have any issues with the liquefaction. So we are varying from, so at the same time, we can't remove all the water from the soil to make your soil to dry state or unsaturated state in the real field problem. But at the same time, we can be able to do something to maintain a partial saturated state such a way that we need to create a system to maintain the required partial saturation with respect to the type of soil what we are considering. So the focus is only on this area where the accumulated air bubbles making the soil as unsaturated state keep the Skempton parameter B less than 1. So we are basically on this particular area. So how our system is going to mitigate liquefaction. So this is a small background about this problem. I'll just go a little more about what is really happening when you introduce accumulated air bubbles in the soil system. So this is what we are looking. So once your soil is a loose state under saturated condition, you are expecting liquefaction. That happens, your building is going to have a massive distress in terms of settlement or tilt or rotational failure. So we want to mitigate that by the way of doing an induced partial saturation. So it's very simple. We are introducing some accumulated air bubbles in the air voids such a way that the air voids is helping to reduce the liquefaction problem. It's all, we are working in terms of the compressibility concept with the stiffness of this particular system using the so-called something called volumetric strain increment. We are put together, we are bringing it together in the theoretical process, and accordingly, we are trying to make what will be the reduction in liquefaction or enhancement in the liquefaction resistance. So that is what we are. So one, we are playing with the bulk modulus of the system. So as we know that when air has been introduced in the component, it is a fully saturated soil mass. As we know that the density of the soil system under fully saturated soil Excuse me, please mute your mic. Okay. So we are talking about in terms of the bulk modulus. As we know that without air bubbles in the system, your bulk modulus of the system will be more. When the bulk modulus is more, your system is not going to compress more, rather it will introduce more water pressure. So when the bubbles being introduced in the system, bulk modulus is going to reduce. So when the bulk modulus is reduced, the system is subject to more compression, thereby the development of pore pressure is reduced. This is the overall concept about this induced partial saturation. So this has been theoretically expressed, and finally we are bringing into the degree of saturation. So the excess pore pressure generation we can estimate by using the simple so-called volumetric strain with the help of the bulk modulus or fluid bulk modulus. So that is what we are bringing into a theoretical formulation. So with respect to each load increment, you are able to calculate the complete bulk modulus, volumetric strain increment with respect to incremental load. So delta U can be estimated by using the stiffness of the soil system. That is what it is given here. So this has been replaced with the so-called bulk modulus Kf, and finally we are just coming with the pore pressure variation in terms of the degree of saturation. So this is what we can able to theoretically see here. Let us come to the method of mitigation of liquefaction induced earthquake induced liquefaction risk by induced partial saturation. There are several methods available to make your soil as a partially saturated soil. The fully saturated soil can be made it as a partially saturated soil. Either you can do a direct air injection method, or you can do some sort of microbial induced partial saturation, or you can use some sort of chemical methods to make air bubbles or gases inside the soil mass, such a way that part of the water molecules can be replaced, or you can go with the electrolysis process. So for this particular study, we have taken direct air injection and microbial induced partial saturation. I'll try to emphasize with these two methods in a detailed manner. So it is basically a pure experimental study. It started with identification of liquefiable soil. Accordingly, we have selected the soil, sandy soil. This is the very narrow grade. So almost it's a poorly graded soil. It's a very narrow range of particles. So having more liquefaction accessibility, it's a poorly graded soil. And non-plastic soil, having the value of Emax, E in this range, and the values of Cu and Cc witness that the soil is poorly graded one. So we need to create air bubbles or gas such a way that the gas will try to replace the part of water molecules in the system. So we identified a particular PCS is called Pseudomonas sutrescis, and this particular bacteria will produce a nitrogen gas, and there are certain advantages with the nitrogen gas because of, so in order to have more effectiveness in the replacement, we were trying to use this particular bacteria to produce nitrogen gas. So we did a complete batch study and how this complete formation about this nitrogen. So this is a chemical process. Finally, we were trying to get this nitrogen gas. So why nitrogen gas? It is a low soluble one and chemically inert, non-combustible gas and non-greenhouse gas. So having a lot of advantages using nitrogen. So we have selected this particular gas for our calculated tablet. It is a small batch study. We can see here how this production of air bubbles and the growth rate, all it is witnessed through this confirmative analysis. And finally, we witnessed that the production of nitrogen gas is possible with maximum change was observed in 2 to 3 days. And bubbles begin to appear on the 3rd and 4th day. So maximum density of bubbles with the size range from 1.1 to 0.3 millimeter. And area of saturation can be controlled by the nitrate concentration. So with this background, we have done the confirmatory analysis for various concentration of taken the initial concentration for a certain amount, and we have maintained a corresponding void ratio of 0.702. And over a period of 2 to 3 days, it's monitored continuously, and how much degree of saturation able to get from the soil system was measured, and the corresponding change in pH value also checked in order to maintain the environmental related issues. So we have also checked with the temperature variation, what kind of impact is having on the air bubble production or nitrogen production of this Pseudomonas bacteria. So normally identify the 30 days no formation of bubbles with 27 degrees Celsius centigrade, 30 days is no formation. 37 increase the temperature, 30 days formation of uniform bubbles and retain. And the temperature is increased to 47 even with the less duration of 30 days formation of bubbles and retain. So these are all the confirmative analysis, and you can see here how it has been. You can closely look at the formation of bubble, calculated bubbles. So this is what the biogas we are intended to develop to create a unsaturated state. So let us move a little more on the degree of saturation calculation. So we know that from the concept of volumetric strain and bulk modulus, we are trying to calculate the pore pressure development with respect to each change in degree of saturation. So we have made a correlation between pore pressure, parameter U, and the previous slide, and the variation of degree of saturation, we have made it in correlation. So theoretically, so finally we want to get the degree of saturation. The degree of saturation with respect to pore pressure parameter, the so-called B value. So that is what another existing literature is on that. This analysis of further extended. Finally, we want to calculate everything in terms of degree of saturation, and the degree of saturation with respect to the dissipation of pore pressure or dissipation of water from the soil system. So the parameter B changes quickly right in the range of degree of saturation 80 to 100. The pore pressure parameter B is therefore found to serve as the good parameter to evaluate the state of saturation for partial saturated soil. So hence theoretically we have already witnessed the parameter B is the one responsible to state about your soil whether it is partially saturated or fully saturated. If the parameter is close to 1, we normally call it as the soil is fully saturated. So this is the normal range with respect to the degree, fully saturated soil means. Some soil may have a full saturation with even with small white space. So that is what you have seen in the previous slide, where we are talking about the transition zone from unsaturated to fully saturated state. So huge variability, and the variation is highly exponential in terms of the variation between 80 to 100. So the pore pressure parameter B is the good measurable quantity. This can be easily measured through any cyclic reaction process. So the quantity of B can be directly reflected the value of degree of saturation. So this is the one theoretical background we have developed. And finally, the degree of saturation will be expressed in terms of coefficient of compressibility of air and water. It's well-known parameter, and void ratio and porosity of the index properties of the soil is a known parameter, and the pore pressure parameter is the P. B is the one going to play with the value of SR because all other parameters are. So this is a simple theoretical process. By means of measuring the B, we can able to calculate the value of degree of saturation. So look at the scenario in this particular degree of saturation with the pore pressure coefficient. It's a very, very narrow range where we are talking about from somewhere, if you look at here 85 to 95 or 97, it's a very, very marginal, very, very gradual improvement of pore water. The coefficient B, pore pressure parameter B, or a larger variation in degree of saturation. But degree of saturation is going beyond 97. There is a great exponential variation of your pore pressure parameter. So as long as you are working your soil degree of saturation less than 85%, the pore pressure parameter is just 0.1 or less than 0.1. So this kind of soil doesn't have any liquefaction potential. It won't liquefy. It is a safer soil because your soil degree of saturation is very, very less. Even increasing the degree of saturation up to 90 or 95%, the risk is almost insignificant. Where we are talking about the problem is where the degree of saturation is increased beyond 95% or 97%. There is a huge possibility where we need to mitigate the soil against the liquefaction problem. So this is a general expected response developed by many researchers. And we have also developed with a conventional theoretical estimation for this particular case. And it's very much close to that, the calculated one, expected one. It's following in almost in the same line. So the theoretical estimation is well validated for this particular condition. So everything we can control in terms of degree of saturation, that is what we finally conferred from this analysis. So from this theoretical background, theoretical analysis, we confirm that making a reduction in degree of saturation somewhere close to less than 90% or 85 to 90%, the pore pressure increment, the pore pressure parameter value is not increasing beyond 0.2 or 0.25. So where we could be able to very much control the liquefaction problem. So we made a small modification in the existing cyclic reaction apparatus such a way that we could be able to measure the degree of saturation through the dissipation of pore pressure during the time of cooling. This is what we did. Just the criteria for liquefaction. So basically, there are two criteria specified. One is the stress criteria, the other one is strain. When the stress criteria, there is a pore pressure ratio, it is RU denoted by delta U by sigma C dash. Delta U is the incremental pore pressure with respect to increasing confining pressure. So normally this RU value, when it is reaches to close to 9 or more than 9, your soil will having the liquefaction problem. So this is the first criteria. You need to keep on monitor the value of RU through this cyclic reaction test. When RU is reached more than 0.9, you can say that your soil is having the potential of liquefaction. So this is basically stress criteria. Whereas a strain criteria is a double amplitude axial strain, dA epsilon A, whereby failure occurs once the sample has accumulated a DAV of 0.5%. So the double amplitude axial strain is the peak-to-peak strain developed during the movie. Anyway, you can see the subsequent slides about this mechanism. This is a very well-known CRS calculation. So the cyclic stress ratio can be range 0.2 to 0.4. It's computed considering the earthquakes such as Chamoli, Muthukkumaran, and Indo-Burma border earthquakes. Some of the case studies, some of the earthquake magnitude we have taken. So based on that, we have calculated the value of CSR, cyclic stress ratio. For these earthquakes, the calculated CSR value is close to 0.2 to 0.4. So this we have taken as an input for the cyclic reaction apparatus. So this CSR we have simulated in the laboratory, such a way that the simulated CSR value of 0.2 to 0.4 is resembling the earthquake condition of Chembali 6.4 magnitude and Uttaragasi 7 and Indo-Burma were 7.2 magnitude scale. So this is what we basically did in the laboratory. Okay. Straight away I'll move on to the results. Just to have a look of, we have basically selected different densities, relative density 30, 40 and 60. So basically 60 comes under medium, the 30 is loose, 40 is the boundary between medium and loose condition. So the selected samples are more prone to have a liquefaction. So by doing this experimental study, we have understand how this mechanism is taking place. So what you are seeing here, untreated, treated. So UNL is untreated, TRL is treated, and 50, 75, 100 pertain to initial confining stress. So 50 kPa, 75 kPa, 100 kPa selected for 3 trials. Here the soil is 30% relative density soil. So as the well-known fact is, if the confining pressure is increased, it will increase the strength of the soil. So DBT stress is also increasing. And looking this solid line and dotted line. So dotted lines are treated soil. It's always above the solid line. So we have gained the strength. This is in terms of only the strength improvement with respect to treated soil. And increasing confining stress will obviously increase the strength of the soil. It's a simple logic. So coming to this pore pressure variation, pore pressure parameter, pore pressure ratio RU value, as we mentioned earlier, when the RU values reaches 0.9 or more, your soil prone to have a liquefaction. So these solid lines are pertaining to untreated, and the dotted lines are pertaining to treated soil. So it is very clear that irrespective of the confining pressure, what you have considered, all the untreated soils are subjected to 0.9 or more than 0.9 pore pressure ratio. So these soils are prone to have a liquefaction, even increasing confining pressure. But whereas the treated soil, here the treated soil is only introducing air bubbles. So bio gases, nitrogen gas by the first MIPS method. So maintaining pore pressure ratio not more than 0.5. So your soil is well resisting the phenomena of liquefaction. So that has been witnessed with all other cases for increasing 40% and 60% relative density. So finally, you can see here in terms of degree of saturation with the confining pressure. These three plots are pertaining to varying relative density 30, 40, 60 and for same confining pressure and degree of saturation. So you can see here the ratio of undrained shear strength ratio with respect to confining pressure. It's very much expected, and the stability ratio also what we have expected is completely prone to have a liquefaction for untreated soil. Coming to the second criteria of strain. Now the strain has been measured. What you are seeing is with respect to number of cycles, pore pressure ratio RU. RU value has reached close to 0.7, having numbers close to 13. And similarly, if you look at this other plot, even for the number 9, ninth cycle itself, it has gone to 0.9. Where you measure the double amplitude strain rate, even having a 8th cycle, it has reaches to 5%. And even this is after having a 13th cycle, you are having only 2% of double amplitude ratio. So one is where you treated the soil, you are trying to reduce this strain criteria, thereby your soil is not liquidable. So both the stress criteria also checked, strain criteria also checked in the treated soil. So treated means is only unsaturated soil is very much having a liquefaction resistance. So this is a further explanation with all the conditions. It is properly witnessed with the selected CSR value of 0.2 to 0.4. The partially saturated soil is having a very good liquefaction resistance than fully saturated soil for the same relative density for the same confinement stress. Stress being presented in terms of the number of cycles, where you're talking about degree of saturation variation. For example, if you talk about degree of saturation, relative density 20%, the soil is very loose state with varying degree of saturation, and the mobilization of cyclic stress ratio, where you're, the word presented in the vertical axis, for the narrow range of 92 to 93, the narrow range of 98 to 99. So this comes under completely fully saturated state, whereas this is 92 to 93 fully partially saturated. Even you can see here, having a narrow range of varying in number of cycles, and the development of cyclic stress ratio is very much exponentially increased, but there is a significant reduction in core pressure parameter, thereby the chance for liquefaction is reduced, even though you are dealing with the 20% related density. The same trend was extended for other relative density 30 and 40. Or other words, you can say here, for example, if you consider this particular plot in the bottommost plot, we are looking into the narrow range of number of cycles. You see here somewhere 100 to 200 or 300 cycles we are dealing. 100 to 300 cycles. The cyclic stress ratio CSR, what we have given as an input, so huge variation of your earthquake magnitude. So CSR is representing the type of earthquake magnitude what we have considered from the case study. So somewhere from 0.1 to 0.5. So 0.1 to 0.5, 0.5 comes under severe, probably 7.2 or 7.5 magnitude we are dealing. So you look at here, if the degree of saturation is maintained as much as low, 90 to 95, even though your earthquake magnitude has increased drastically, somewhere from 5.5 magnitude to 7.5 magnitude, but still we could be able to maintain the dA epsilon A less than 5%. The double amplitude axial strain is less than 5%. Your soil is stable, it is not reaching to any liquefaction risk. Whereas the degree of saturation is increased. So this is almost like a fully saturated state, but even having a small number of cycles. So where we are talking about 100 to 300, but here similar magnitude, but the numbers are so less, somewhere 10 to 80 or 70, we are reaching the same amount of liquefaction resistance. So that shows very clearly, introducing partial saturation in the soil. Suppose if you are going further reduction in degree of saturation, then we were able to reach even further earthquake also, more than 0.5 CSR also we can reach with a very controlled way of the so-called dA epsilon A less than 5. I hope this has given a complete idea about the criteria. So next method what we have selected is direct air injection. So same modification what we did, the cyclic reaction apparatus, able to inject the air on the sample, and expelled water have been measured. Through the measured water, the degree of saturation were calculated. That is the concept. So we did a sample exercise maintained with the relative density of 20, 30, 40. And this is an air injection pressure. It's a controlled air injection pressure, 5 kPa to 10 kPa for different durations have been used. And so this is, we have maintained with the 2857 two sample size. And the water expelled quantity was measured. And through this measured expelled water quantity, the degree of saturation was back calculated using the theoretical process. So since the air injection is pressurized with some air pressure, that should not create any visible cracks in the soil system. So once the cracks have been developed in the soil system, soil will be, it will loosen its strength. So that should not allowed. So continuously the air bubble injection was monitored and the visible cracks was noticed. Fortunately, no cracks were noticed for this particular condition. So this condition has been stabilized. So we used a simple theoretical background to maintain this air injection pressure such a way that the pressure is always less than the overburden pressure of the soil. That is what the condition is stabilized. So then the air injected soil, we have done the same test as what we did for microbial induced biogas. Similarly, the tests have been conducted and notice the double strain amplitude as well as the stress criteria. So this air injection also is very much satisfied with respect to liquefaction reduction, precipitated reduction or increase in liquefaction resistance for treated soil. So finally, this is what we have developed for the cyclic stress ratio, cyclic resistance ratio with respect to degree of saturation based on the experimental result. This has been given, and the CR value increased from 0.165 to 0.412 for degree of the compaction relative density for 10%, 20%, 30 and 40, and for it's stated in terms of 100 to 85 degrees of separation. So these were plotted for 3 selected relative density and saturated and partially saturated soil specimen with a range of degree of saturation from 100 to 85 for 100 kPa confinement stress. And from this, the liquefaction factor of safety was estimated by considering the so-called conventional method given by NIT Trichy. And based on that, we have identified and selected. So this results, calculated factor of safety was directly related with the peak ground acceleration. And accordingly, so we have brought out the boundaries with respect to PGA, so peak ground acceleration is the direct measure of the earthquake for varying degree of saturation. You can see here the degree of saturation, what it has been mentioned with different color. The bottommost what you are seeing is 100% saturated, and the topmost is 80. So the variation is almost like every 5% variation of degree of saturation. And where we are talking about the factor of safety. So as if you look at here, this is the boundary under equilibrium condition where the factor of safety is considered P1. And normally for any designer may expect to have a factor of safety of 1.5. So if you take this 1.5 as upper limit, and this is a boundary what we are considering for our problem. So anything below this is taken as a dangerous one where you are expecting liquefaction. So above this is a stable zone. So Now we are just playing with this degree of saturation with the peak ground acceleration, what you are expecting from the earthquake. So, to maintain this high factor of safety, it is very obvious that you need to have a very less ground acceleration. So this ground acceleration is with respect to the type of earthquake magnitude what you are considering. So more the acceleration, less the factor of safety. It is inverse relation. But as long as when you are dealing with more saturated soil, irrespective of your PGA, your soil is subjected to liquefaction. Even having a small earthquake, your soil can liquefy. Okay, so increasing PGA, it's very obvious your soil is having a liquefaction. Prone to liquefy, you have no problem. But that has been mitigated with respect to reducing the degree of saturation. And this particular plot is pertaining to 20% relative density, whereas 20% treated to be a highly dangerous one in terms of the soil compactness composition considered. Suppose if you increase the degree of saturation reduce the degree of saturation from 100 to 95, you are slightly increase the factor of safety. 95 to 85, you are further increasing the factor of safety. 85 to 80, you are completely from the border. Even if your magnitude is very high, where it has a peak ground acceleration close to 0.35 g, or even slightly more than 0.35 g, so where we are talking about a high magnitude earthquake, still you are able to protect your system against liquefaction because your factor of safety is close to 1.5 or more than 1.5. You are well within the system. So this is what we developed with respect to the induced partial saturation concept. So how much you need to create an induced partial saturation, whether you want to work the problem with 80% saturation or 95% saturation, is all with respect to the expected PGA value. This is pertaining to 20% relative density. Likewise, we have developed for 30 and 40. And this is further, it is summarized in terms of the impact. And this whole study, we are intent to check the durability aspect as well, because the air bubble supply is supposed to be a continuous process. So we have checked the complete durability aspect as well for a long period, how we could be able to maintain. So this is the system we have developed. All these are patented to work. Recently we obtained patent for this work. So how we have, the air bubble injection, we have tried with all the means, bubbles from the horizontal direction, bubbles from the vertical direction. And we were trying to identify the effective mechanism where we could be able to get maximum expulsion of water with a short period of time. And moreover, the durability aspect. We want to retain the accumulated air bubbles for a longer period, it should not burst. So the durability aspect studied for a longer time, up to 1 month we did the study. And the fluctuation is more or less same, not much variation, except a few places, both the air injection as well as biogas. We also checked with the varying temperature, considering the field condition, it's not much variation. So this we have extended to a film analysis. Flat, I'll just skip this. So this is the air injection delivery for a different system what we have considered, and the effectiveness of the system was studied and identified the suitable application methods. This is the complete result of that. So this is what we are proposing for the field study. So suppose you have an existing building where your subsoil is prone to have a liquefaction. It is under saturated condition. So we have developed a system, and this system is also fully automated system. So with the system supposed to calculate what is the soil confining stress, what is the degree of saturation, and what is the void ratio, what is the compactness, whether it is loosely packed, medium or dense. So all these things will be automatically calculated by the device. Then with respect to the required soil condition, there will be an automatic air injection process. So the air injection process will be complete monitoring system. We have a computer monitor system. So that monitoring system will take care of how much air injection is needed to maintain a particular degree of saturation over a period of time, such a way that your soil will be always kept under partially saturated condition. Whenever earthquake comes, your system will accelerate. It will inject the voids on the system, and it always kept the soil as a partially saturated condition. This is the complete development of automated system. You can see how the air bubbles are produced. It's a very thin holes, 0.1 to 0.1.5 millimeter diameter holes, continuous air bubble system. And the air bubble is supposed to maintain. You can see here, this is the propagation of air bubbles in the fully saturated soil mass. You are seeing the color change. This is the propagation of air. So with respect to the propagation of air, your water is being displaced at the top. So it has been partially removed. So your soil is maintained with the partially saturated. So with that, I have come to the end of my presentation. So all the discussion were comprised as a conclusion in this slide. So I'll stop my presentation here. If you have any questions, please. Over to you. I've done the presentation. If you have any questions, please check the chat box. If somebody wants to ask any questions, please unmute your mic and ask a question.
Hello. Very good morning, sir. Hello. Sir, actually, I have one question.
Please.
Sir, I want to ask that what will be the minimum value of magnitude of earthquake to trigger the liquefaction in the partially saturated sand, sir?
You are talking about this particular plot?
Yes, sir. Yes, sir.
Okay. So actually, you remember earlier we have taken the whole process with the 3 earthquake. Chamoli earthquake,
Yes, sir.
which is
Yes, sir. Yes,
6.6,
sir.
Uttarakhasi 7, and Indo-Burma 7.2. So this is the range we have selected. For this magnitude, the corresponding CSR value is 0.2 to 0.4. So this is what our input parameter for the cyclic reaction study. Okay. So this covers close to 6.5 to 7.5.
Sir, so there is no criteria of the magnitude of earthquake. Suppose in the Bhuj, the magnitude of earthquake is different. In Gujarat, there the buildings are also collapsed due to the liquefaction.
Yes. Gujarat is slightly, I think, 7.5. Huge earthquake.
Okay, sir. Okay, thank you, sir.
Yeah.
Thank you, sir.
Any other questions?
If any participant has any question, please raise your hand or write in the chat box. I think there are no other questions.
Okay.
Thank you, sir, for a wonderful session. We have gained a wealth of knowledge about earthquake and soil, which will surely add a great knowledge in our future. Thank you once again. I'm requesting all the participants, please turn on the camera for a group photo. Thank you so much.
Thank you all. Thank you.
Thank you, sir.
All the best.
It's our pleasure to have you. Such a good knowledge. Participant will update tomorrow's session details on your WhatsApp group. Thank you.